So I want to use some of these general results that we learned about general group homomorphisms to understand cyclic groups. So prove certain things about cyclic groups. And you can prove these things directly. You don't have to use homomorphisms. But I just want to illustrate how this language can become useful. And I also think it makes the arguments cleaner. So remember, a cyclic group means a group G where there is an element in the group so that every element of the group can be written as some power of this A. So if you take A and take all its powers, identity is A to the power 0, and then also the inverses. If you write down all these elements, this list exhausts all of the group. We're not saying all these elements are different, but that this covers all the elements of the group. Okay. So let's start here with the first result. It says that if you have a group homomorphism from a group G to group H, if this homomorphism is onto, surjective, and if the domain group is cyclic, then the target group H is also cyclic. So image of a cyclic group under a group homomorphism is again a cyclic group. And this sort of is in the spirit of these results that I was talking about, that when you have a homomorphism between two groups, sort of builds a bridge between these two groups. So if you know something about one group, you can conclude something about the other group. Here, you know G is cyclic and you're concluding that H is cyclic. And this is very straightforward. So choose a generator for G such that G is generated by A. So then G, all elements of G look like A to the power something. And I'm going to claim that if you take the image of this element under F, that guy is going to be a generator for H. So just image of a generator is a generator. So let's call this guy B. And now take, what do I have to show? I have to show that if you take anything in H, take a little h in H, then it's some power of B. Now since F is onto, you can write H as some F of something. This something is an element of G, but all elements of G look like A to the power something. For some n, since G is, all elements of G look like that. Okay. That's just said for emphasis. But then this H is same as f of A to the power n, which is B to the power n. So H is some power of B, so H is generated by B. You showed that every element of capital H is some power of B. By the way, this equality uses the homomorphism property. You see, f of A square is f of A times A. By homomorphism property, that's f of A times f of A, which is f of A square. Similarly, you get f of A cube equals f of A cubed. And you also know, we proved this a while ago, that the inverse of fa is f of A inverse. So if you use that, you also get this for negative n's. Okay. So at any rate, that's the proof of 1. The image of a cyclic group under a homomorphism is cyclic. The second thing I want to record is that every subgroup of integers is cyclic. This we know already because the subgroups of Z, we listed this before. Z are these guys. There's the 0 subgroup. There is 1 times Z, which is Z. There is 2 times Z, which is the even integers. There is 3 times Z, which is the multiples of 3, etc. This is generated by 1. This is generated by 2. This is generated by 3, etc. So all these are cyclic. So every subgroup is cyclic. Okay, this we knew already. 3 is a sort of a, not a fact about cyclic groups, This is about constructing homomorphisms from Z. And this is basically saying that constructing homomorphism from Z is easy. That's how I want you to remember it. Constructing homomorphism from Z is easy. Meaning all you have to say is where 1 goes. 1 is an element of Z. So to make a homomorphism from Z to some group, all you need to do is choose an element and say that I'm going to send 1 there. You can send 1 to whatever you please, and once you know where 1 goes, everything else is determined, because once you know where 1 goes, 2 has to go to a square. Again, because of the homomorphism property, you see, because f of 2 has to be f of 1 plus 1, which is f of 1 times f of 1. By the way, the operation in Z is called plus, whereas in a general group, we write it as a dot. So that's why the plus here and a dot here. So that has to be a square, etc. So once you know that 1 goes to A, 2 has to go to a square, 3 has to go to a cube, etc. So I'm just going to say sketch define f from Z to G by f of n equals a to the n for all integer n, and verify this is a homomorphism. Why is this a homomorphism? That amounts to just saying f of m plus n equals f of m times f of n. Is that true? This thing is a to the m plus n, and this thing is a to the m, a to the n. A to the m plus n is a to the m times a to the n. So this is indeed true. Yeah. So I'll let you write this out. And now check that it's, so we check that it's a homomorphism. Now verify that there is only one such f. Meaning if you have two things, f1 and f, both from integers to G, such that both take 1 to A, then f and f1 have to be the same. Because you have no freedom, basically. Once you know where 1 goes, you are forced by the homomorphism property to send everything to a specified place. Okay, that's why the uniqueness. So this shows existence. Uniqueness is going to be an exercise. Okay. Anyway, I only need the existence for the next one, which says that if you have a cyclic group, then you have an onto homomorphism from integers. And this follows from the previous one. You just choose a generator, A, such that G is generated by A, and then by 3 there exists a homomorphism F from integers to G such that 1 goes to A. So then f of n is a to the n for all n in Z. But every element of G looks like a to the n for some n, because G is generated by A, you see. So that shows you that f is onto. This f is onto. Okay, so this is going to be crucial, that if you have a cyclic group, it has an onto homomorphism from integers. And now let me just tell you in picture why this probably deserves the name of a theorem. Every subgroup of a cyclic group is cyclic. So you take a group, H maybe, and take some subgroup, M maybe. So H is cyclic. And I want to show that M is cyclic. Okay. Because H is cyclic, there is an onto homomorphism from integers by 4. Onto homomorphism exists by 4. All right. So now you take the pre-image of this M. So look for all the integers such that when you apply F to them, they land in the shaded part. This thing is called F inverse M. And a lemma that we proved last time, which I have recorded here, says that if you have a subgroup on the right hand side and you have a homomorphism, the pre-image is also a subgroup. So this is a subgroup of Z by lemma from before. This we did prove in detail. Okay. Now that you know this is a subgroup, you also know it's a cyclic subgroup by 2. By 2, F inverse M is cyclic. Okay, it's a subgroup of Z, so it's a cyclic group. And now you notice that this M is, after all, F of the pre-image, because F is onto. This you have to verify. Because F is onto, every element of M is image of something in Z, but that something by definition lies in F inverse M. So every element of M is F of something in F inverse M. It's almost tautological. So M is F of F inverse M, so it's the image of a cyclic group under a homomorphism. So by, which one was that? 1, right? Image of a cyclic group is cyclic. By 1, M is cyclic. So I think that's a decent illustration of how these concepts help. Maybe I should talk quickly about the structure of cyclic groups in general. Structure of cyclic groups. G, generated by some element A, let's say. So case 1, when G is infinite, how does this group look like? Start with the identity, multiply by A, you get A. Multiply by A again, you get A square. Multiply by A again, you get A cube. Keeps going on forever, never comes back because it has infinite order. On the other hand, you could multiply by A inverse, and that would go the other way. So this is what it looks like. So this is A to the 0, A to the 1. So you can see basically that this structure is same as the structure of integers. So in this case, G is isomorphic to Z, you can prove. In fact, just sending A to 1 would be an isomorphism. And now case 2, let's say G has order n, meaning size n. Size of G is n. Size of a group is called the order of the group. Okay. In that case, I claim, or at least let's say this generator has order n. That we have defined already. Yeah, so this here the generator had infinite order. In that case, G is infinite, in fact isomorphic to Z. And now let's assume that it has finite order n. So let's say n equals 5. Then how does your group look like? Start with identity, multiply by A, you get to A. Multiply by A again, goes to A square. Multiply by A again, goes to A cube. Multiply by A again, goes to A to the 4. Multiply by A again, goes to A to the 5, which is the identity. Because that's what order 5 means. But not before that. So you get these 5 things. And this structure is same as the structure of Z mod 5, you see. You have 0, add 1, 1, add 1, 2, add 1, 3, add 1, 4, add 1 again, goes back to 0. That's Z mod 5. So matching them up like so shows you that's an isomorphism. So in this case, G is isomorphic to Z mod 5. And you could change 5 to n. So if, more generally, if it has order n, then G is isomorphic to Z mod n.